Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will understand support vector machine classifier. So support vector machine, it's also known as SVM. It can be used for both classification and regression. So in current video, we will understand support vector classifier, right? So let's understand for geometric intuition and then we will derive a mathematical formula for it. Okay. So we had learned in logistic regression that on the classification algorithm, we need to find a best line or plane which can divide our labels, right? Basically classes, let's say positive and negative classes, right? So if you haven't watched my logistic regression video, please check it out. It will help you understand SVM, right? So let's say what logistic regression do, right? We need to find the best plane or line which can separate my data points, right? So we can draw multiple planes which can separate these two data points, right? Let's say I can draw a line this line also separate both points, right? This is also possible. This is also possible way, right? So there are multiple planes or lines which can separate our classes in the geometric region, right? But what SVM aims for? SVM wants to find plane which can separate my positive and negative point as far as possible, right? So let's say, let me draw two lines right here. So let's say I am drawing one plane which can pass through a point, or we can say first point. Let's say, let me put it this way. So this is our positive class and this is our negative class, okay? Okay, so I'll draw first line which is passing from a first negative point of this data, okay? And now I will draw a second line which is parallel to this line and passes through a first positive point, right? So let's draw that. Okay, so these two lines are parallel. Okay, so my best line which can differentiate these 2 points would be this, right? Which is, I can say, equal distance or as far as from my first negative and from my first positive point, right? So let's say this is my plane P, okay? And let's say I call this P minus and this is P plus, okay? So basically this is the plane or line which is passes through the first positive point, and this is a plane or line which is passes through the first negative point, okay? Or number of points which are in this line, right? So first of all, let's see these points, right, from which my P plus or P minus plane are passing are called as a support vector. This is basically a vector, right? In 3-dimensional it is 3D vector, in 4-dimensional it would be a vector with 4 values, right? So these are the support vector, can say, in support vector machine, okay? So now the task of SVM is to find this distance and maximize this distance, right? And this distance, also called, let's say, distance between positive plane and negative plane, is called as a margin, okay? And this SVM solve the problem using, we can say, margin maximization. Okay, so SVM tries to maximize this margin, basically distance between positive plane and negative plane, right? And for prediction, we will use this plane, right? This p plus and p minus we are taking as a reference to find maximize margin. So to find a plane which can separate my positive and negative point as far as possible, or this distance could be as wide as much, right? Okay. So let's say what would be the distance between these two planes, right? So in logistic regression, we understand that plane, right? Let's say P1, let's say this distance is from this plane, it could be at the one distance, just assuming that, right? So let's say this P is, let me write it again. Let's say this P is W transpose X plus B is equal to 0, then my P plus will be W transpose X plus B is equal to 1, and P minus will be W transpose X plus B is equal to minus 1, right? Because my normal vector or my W is in this direction, right? So this W is perpendicular to both planes P minus and P plus, right? So whatever in this direction would be positive and whatever in this direction would be negative, right? And yes, our class is also yi belongs to minus 1 and 1, right? As logistic regression we had learned that yi could be minus 1 or it would be plus 1. So for positive, let's say it's 1, and for negative it's minus 1. So these are the formula, right? So now we need to find the distance between these two planes, right? P plus and P minus. Okay. So what would be it? So let's say in this equation for P plus, let me write it here. P plus is equal to W transpose X plus B is equal to 0, right? Here if I put X is equal to 0, then I will receive, sorry, P plus equation is not 0 but 1, right? 1. Then I will get B is equal to 1, right? Now just remember this, and let's say I can write P minus is equal to W transpose X plus B is equal to minus 1, and again I can rewrite it as W transpose X plus B plus 1, right, is equal to 0, right? This is the equation, basically AX plus BY plus C kind of thing, right? Simple. Okay, so this is P minus, right? Now I want to find a distance of this point where X is equal to 0 from this plane, right? So what would be it? So we know the distance of the point from the plane, we can write it as a W transpose X plus B plus 1. Here the formula of the plane is W transpose X plus B plus 1, right? Then, okay, let me draw like this. Okay, W transpose X plus B plus 1, which is nothing but P minus plane and norm of W, right? So if you put X is equal to 0 and B is equal to 1 here, from here, right, we find while putting X is equal to 0, we found B is equal to 1. So D would be 0 plus 1 plus 1 divided by norm of W, and it can be written as 2 divided by norm of W, right? So this is basically a distance, or we can say a margin between two planes, right? And here is a constraint is that our yi and yi is belong to minus 1 and 1, right? So we had seen in logistic regression that yi into W transpose X plus B in logistic regression it was greater or equal 0, right? because y, if negative, we are classifying this as a negative and we are multiplying it with a negative class which is yi, then it would be positive. And if there is positive class, we are predicting it as a positive and we are multiplying it a true level which is positive, then we will receive positive value, right? So it would be greater than 0 in logistic regression. But here our plain formula is, in logistic regression we have this like w transpose x plus b is equal to 0, but here instead of 0 we have 1, right? So we can write, here is a one constraint such that w transpose x plus b should be greater or equal 1, right? So if you see in this graph, so we are maximizing this distance, right? So we are finding a plane from every point r at some distance, right? If we use this plane and assuming all points are beside this and all points are beside this plane, then from this plane any point could be at the distance of greater or equal 1, right? In this case minus greater or equal 1, in this case positive greater or equal 1. But we are multiplying it with yi, then it would be greater or equal 1, right? For simplicity we had took 1 here, right? But you can put any number. If you put, let's say, w transpose x plus b is equal to k, then you will end up with this equation, norm of w, right? You need to maximize this. So what problem SVM is solving? Let me write it this way. Find best w where maximize, let's say we are doing argmax 2 by norm of w, and there is one constraint is yi into w transpose xi plus b should be greater or equal 1, right? So this is a main motive or optimization problem for SVM, right? But we had seen that in machine learning we are not maximizing something, but we solve the problem in terms of minimization, right? So if I say, let's say I am maximizing n, right? So I can say I am minimizing 1 by n, right? This can say, right? So I can rewrite this equation that w star, find the optimal w which will minimize norm of w by 2 and same constraint will not change, right? That yi into w transpose x plus b greater or equal 1, right? So this is the optimization problem for SVM. Okay, so here if you see, this is the formula, right? First let's see, let me put it this way so it will be highlighted. Okay, so here if you see, in our constraint there is one problem, right? We are saying for each y or for each point we need yi w transpose xi plus b greater or equal 1. That means our all data point should be separated linearly, perfectly separated, right, in linear space. So we cannot say that any blue point is in this region or any red point is in this region. So there should be no misclassification happen, right? And if you see that in real world we will not find any data set which is perfectly linearly separable, right? There would be some errors. So we need to modify this equation so it can allow some errors. And by the way, this is called as a hard margin SVM. Hard margin SVM. Why? Because it has some constraint which is very hard to achieve, right? we want our data set perfectly linearly separable, then and then this optimization will happen, right? We are not allowing any error or any misclassification here. So let's modify this equation. Okay, so let's say this was my equation, right? Let's say find optimal W which will minimize norm of W by 2. Constraint is yi W transpose xi plus b greater or equal 1. Okay, so here we can add one term. Let's say I am writing new equation here. We are minimizing plus c times 1 by n sigma I is equal to 1 to n eta. Okay, so this is eta. So what is eta here? So I can say eta will be greater than 0. It would be greater or equal 0 basically, but eta will be, let me write it here as well, eta would be greater than 0 for misclassified point, right? And eta is equal to 0 for correctly. Let me write it in proper space. Okay, let me write here. So basically eta will be greater or equal 0, but I can say eta will be greater than 0 for misclassified point, right? And eta will be 0 for correctly classified point, right? So you can think eta as in a loss or error, right? And in this equation, if I say, we can think in this direction. Let's say yi into W transpose xi plus b. Let me write below, it would be better, right? Let's say yi into W transpose xi plus b, we need greater or equal 1, right? But we can say eta would be here. So what would be the eta? So let's say while doing yi W transpose xi plus b, I am getting distance minus 2, right? But we want greater or equal 1, right? So then I can write it as like 1 minus 3. I can replace this 2 by 1 minus 3, right? So this will be our loss, or let's say error. Let me write, okay, error, right? This 3 is error because we want 1 but we receive minus 2, so there is a 3 error in any unit, right? So this is the error. So just we are writing here error. This is eta. So basically this term is error distance of the point which are misclassified, right? Average distance of the point which are misclassified. And what is C here? So C is hyperparameter hyperparameter, right? So we can tune this C, right? Okay, so let's understand the impact of C here. So now our SVM equation is find optimal W which will minimize norm of W by 2 plus C times 1 by n sigma I is equal to 1 to n eta I. Okay, so for each point we are just calculating the average distance which is for a misclassified point, right? So, and this formula called as a soft margin SVM, right? because we are allowing some misclassification while finding a best plane. It don't use any hard assumption, right? So it's called as a soft margin SVM. In real world, we are using soft margin SVM, right? As we know, like hard margin SVM is hard to optimize, right? Because in real world, we will not get any data set which is perfectly classified or perfectly linearly separable, right? We will always get almost linearly separable. So this called as soft margin SVM. Let's understand the C. So if you increase the value of C, let's say increase C, then what will happen? You are allowing you are providing more weight to this part, right? Basically this part. But what is this part? This part calculating the error, right? So if here we are making small error and if C is larger, then it will become larger, right? And we are solving minimization problem. So we will not allow any error when our C value is higher, right? So increasing C can be result in overfitting, right? Because while training, if it not allowed any misclassification, then model will overfit our dataset, right? It will not generalize, but it will solve only training problem. Same, if you decrease C, right? So this part will be, we are providing less weightage to this part. If C, let's say we are putting C very small value, right? Let's say I am putting C is equal to 0.0001, and if any error arrived and we are multiplying it, right? Let's say 1, then it would be very small value, right? So it will not impact much. So we can end up with underfitting. Right? So this is basically a C, which is hyperparameter, which by tuning which uh, uh, we can find best plane which is not overfitting or not underfitting. Okay. So this is all about the SVM, and we need to solve this problem, right? So if you have any doubt or query related to this SVM lecture, you can write in the comment section and we will discuss there. Okay. And if you like this video, please like and subscribe my channel for further updates. In next video, we will create or implement SVM from the scratch using Python. Stay tuned. Thank you.